So my name is Kevin Nelson. I'm a developer advocate with Google. I spend a lot of time looking at machine learning, and I also do a lot of work with SAP on the enterprise side. So if anybody wants to talk to me about that later, I'll be happy to address any questions. It's been an interesting trip for me, actually. I started this trip 3 weeks ago in India. I went to Bangalore, India, and then for an SAP event, then flew from there to London for Next London last week, and then flew in last night into Istanbul. This is going to be the end of my trip. I have to go home on Wednesday for our Thanksgiving holiday, but it's a treat to be back here again. Did anybody see my talk I gave here last year? Okay, a couple of people. You're going to see some slides that are familiar. Don't worry, they're kind of just setting up the story, and we'll get into the new meat of the subject. But I do like to start these talks by talking about how I view machine learning and why it's become important over the last few years. So machine learning generally is used to address two classes of problems. Problems that can't be done at scale, meaning there aren't enough people in the world to do these things, and problems that can't be done at all using traditional programming techniques. A great example of a problem that can't be done at scale is for diagnosing a disease called diabetic retinopathy. And this is a disease that diabetics get in their eye that will eventually lead to blindness if it's not treated. Diabetic retinopathy can be diagnosed very easily by taking what's called a fundus image, which is this image on the right. It's an image an ophthalmologist takes by putting a special camera very close to your eye and taking a picture of the back of your retina. And this works well in places like the United States, where there are lots and lots of ophthalmologists relative to the number of people that are in the population. But diabetes is a problem growing around the world, and in India, for instance, with a population of over 1 billion, there are now forecast to be more than 70 million diabetics in India by the year 2030. And they don't have nearly the number of ophthalmologists available to actually capture and then diagnose these images. So they need new tools to be able to do this. So Google has been working in the healthcare space with leading researchers and has built a model that is able to look at these fundus images and be able then to diagnose whether people are likely to have diabetic retinopathy and suggest that they go see an actual ophthalmologist. So this is going to be life-changing for a lot of people who are not going to lose their sight. And this is one example of many of these classes of problems. Now, for problems that can't be solved at all, there's a classic example of trying to distinguish between a cat and a dog. This is something any 2-year-old can do with almost perfect accuracy, but computers, up until even about a decade ago, were terrible at it. Using traditional programming of trying to analyze what features in the image distinguish between a cat and a dog ended up being very, very challenging. But you can imagine why doing procedural programming to distinguish between a cat and a dog might be a challenge. I mean, right, they both have 2 eyes, a nose, 2 ears, they're furry, they have 4 legs. But what about something simpler? What about something as simple as distinguishing between a dog and a muffin? Now, this seems pretty trivial. Obviously, dogs are these living things that are furry. They have legs and eyes and ears and a nose. A muffin tends to be round, maybe has a dome top, wrapper. But when you get to the edges of the data, you find that the real world is messy. So procedural programming might work for, say, 70% of the cases that are out there. But when you start getting into the edges of this, you end up with potentially silly examples like this, but the reality is that the world is just messy. So whatever your domain is, when you get out to the edges of the data, you're going to find that there's no effective way of doing procedural programming to solve those problems. So now with machine learning and the massive scale available for compute and storage that's come about as a result of the internet and cloud providers, we now can employ vast compute resources on these problems that are incredibly compute intensive to be able to solve. And we've seen this on a number of different domains. A few years ago, Google made some headlines. Actually, DeepMind made some headlines, a company that Google acquired a few years ago, by beating the world champion in Go. That was a version of a program called AlphaGo, and the program was trained on thousands and thousands of games by top players. But then after Google, using this version that we now call AlphaGo Master, defeated the world Go champion, Google threw that away and started a new version that's now called AlphaGo Zero. It was trained from scratch using just the basic principles of the game. You can put a tile down, and then you want to capture territory and go from there. It learned by just playing itself. It started playing randomly and found patterns that worked and got better and better and better. After 24 hours of training AlphaGo Zero, it beat the version that beat the European champion. After a few days, it beat the version that beat the world champion, and it is now the best Go player in the world. And what's interesting about that, I think, is that along the way, AlphaGo Zero rediscovered all of the strategies that human experts have used over the years, but also found several new ones that allowed it to exceed the capabilities of humans. And this is a great example of the fact that as humans, we're biased. You know, a Go player starts training, a professional Go player starts training at a very young age with other experts. They have learned their techniques that work, and they train the person to use those. But it's very easy to miss other strategies that may seem absurd at the beginning, but might yield great strategies later on. And we'll come back to that. Self-driving cars, another example. You know, we see all these examples going on in the world. Communication, if you talk to your phone and say, hello, Google, and I'm sorry, I probably just activated half your phones out there. You know, all these things are built using machine learning models. Even the output speech now. A few years ago, if you were doing text-to-speech, the voice would sound very robotic. Now the voices sound much more human, and that's a result of machine learning as well on matching waveforms on the output. So Google provides a whole series of pre-trained models to do a variety of different things. There's vision for looking at images and trying to understand them, natural language for understanding speech, translation, obviously for translating text between two languages, speech for taking audio and taking the words out of that so that you can then drop that into a database, for instance, and make it searchable, bring that data alive, and then cloud video intelligence. So we're going to do a quick walkthrough through a couple of these before I get to the kind of the meat of what I'm going to talk about today. So the Vision API will do a bunch of different things. It will, if it's a physical object, it will understand where it is in the world. It's able to extract text from those documents, and is also able to tell you whether that image is safe for work. So here's a great example. So I took this image today. I suspect everybody in the room recognizes this, but I wanted to see how the Vision API would do with it. So I submitted it to the Vision API, and sure enough, it comes back and identifies this as the blue mosque. And it's 72% confident of that. You see here 72%. And it tells you where on this image a bounding box of which exact pixels it was using to determine that that was the blue mosque. Then because this is a landmark, it tells you where it physically is. So latitude 41 degrees, longitude almost 29 degrees. And one very important part up here is this MID. MID is the identifier into the Google Knowledge Graph that everything related to this object is put together in this graph that then is linked out to other things. So it would also link to Istanbul. It might link to Islam. It would have other associations so that it has semantic knowledge of how this object fits into the world. And optical character recognition. This is an interesting case. This is in a staircase in the Google Mexico City office. I was there last year. And I was really curious how it would do with this particular image because it's weird colors and text, and I've taken it into a corner so the text is all shown in perspective. So I submitted that to the Vision API, and sure enough, it found all that text. So with these tools, you submit the image and you get back data in JSON format that then you can then do whatever you want with. You can drop it into a database, you can search, sort, you can use it for classification. And basically, it's a way of bringing that data alive as opposed to just having this dead image sitting out there. So let's take a quick look at a demo of this. So this is a page that anybody can go to. This is cloud.google.com/vision. You can go try these things all by yourself. So I'm going to take an image on here, and I'm going to drag it in. I probably need to tell it that I'm not a robot, at least not that when I checked last time. And let's see what we got. So this is an object we all probably recognize, Eiffel Tower, but it turns out that this isn't the real Eiffel Tower. Vision API is telling me that this thing is in Planet Hollywood Resort and Casino. So it turns out that the real Eiffel Tower does not have a building underneath the main arches. So whereas I might have made a mistake in this image, the Vision API is able to go by without the bias that humans have or the carelessness that humans might have to be able to correctly identify this. And let's see what else we got on here. So I can look at labels. It says that this is a landmark, it's a tower, its architecture shows confidence for each one of those. I can see where else on the web I might find this image, which is very interesting, especially if you're trying to do IP protection. You might have some images that you own, logos. You can find out who's using those things. If there's any text in there, we'll extract it. I didn't notice any text in here, but there are a couple of words here that are, even in this low resolution image, it was able to pull something out, but not too useful there. Tells properties about the image, primary colors, if you want to use this for automatically matching backgrounds, for instance. And lastly, safe search, it says, yeah, this image is no problem. Let's look at one more example. I want to look at expressions. So here, the Vision API understands people's faces. It doesn't identify people's faces, but it will extract features, expressions, rotation, angles. So it says here that face 1, joy is very likely. Face 2, not much going on there, but notice the roll, tilt, pan. So this is a great way of extracting information about people, things, places, words that you can use. So I'm going to go back to my slides. So the Vision API is great if the thing you want to identify is something of general knowledge using images that can be found on the web. But what if you want something more specific? So we know that the Vision API is good at identifying between cats and dogs. So if I want to identify whether this image is a cat or a dog, I can use the Vision API and I can get a prediction and says, yes, sure enough, this thing is a cat. But what if I want to know what breed of cat this is? So one simple classification problem. We have to figure out what model to use in order to make a prediction and find out that this particular cat is a gigantic breed called a Maine Coon. But how do we build that model? So how many people have built a model using TensorFlow, built a machine learning model? Oh, that's awesome. I think that's the highest percentage of people in any audience I've seen anywhere in the world. Okay, well this might be a little bit too basic, but we're still going to go through it. So you obviously start by identifying a problem, and then you have to gather and pre-process the data. So you're going to collect a bunch of images, and you're going to classify those. You're going to have some expert go through and tag those images. So you're going to find a bunch of images of Maine Coons, Abyssinians, Scottish Folds, and all the other breeds that are out there. Then once you have that data, you have to split it into your training data set and your test data set. You have to do that because when you're going to test for the accuracy of your model, you can't have it be using data that you already trained on because it already knows those answers. Then once you do that, you have to then build a model. I'm going to give an example here in Keras, but you can do it in TensorFlow or any of the other popular frameworks. But before we dive into that, I just want to make sure for the people who did not raise their hands that everyone understands what I'm talking about. So this is a graphic representation of a deep neural net. It only has 4 layers, but this is a net that we're trying to design to distinguish between cats and dogs. So it shows 4 different layers on there, and initially those layers would be fully connected. Every neuron would be connected to every other neuron at the next level. The training process goes through and figures out which of the neuron connections provide the best predictions at the end. And the ones that are good at making predictions get reinforced, and the ones that don't result in good predictions get trimmed and eventually can actually be removed. And when you build these networks, each layer is designed to do something specific. So it might start out where the very first thing is just to identify edges and colors and group them together. From that, you start looking for specific features of the things that identify your objects you want to classify. In this case, like eyes and nose. Then you might put those together into higher level functions like a face or a leg. And finally, at the end, you get the layer that yields the predictions that you want to do. So these models can get very complex. This particular model has 39 layers. It was a state-of-the-art image classification model from like 5 years ago. Now the neural network that Google uses for recognizing images is more than 100 layers deep, built, hand-built by some of the top researchers in the world. Okay, so now coming back here, I'm going to do this in Keras because it's a little simpler. Keras is specifically designed for neural networks like this. TensorFlow can deal with additional kinds of machine learning, and it just adds a little bit more complexity. So you start out, you have to import several different things. You have to import the type of model you want to work on. You have to import the functions and the convolutional functions that you want to use. Then you're going to build that model. And this basically is the world's simplest neural network that I've defined up here. So I have a sequential model. These are just one layer after another. I'm going to start out with a convolutional 2D, and I'm going to use a 3x3 kernel size. I have to specify my activation function. In this case, it's ReLU, or Rectified Linear Unit. Turns out that is very effective for things in the real world. It's just a linear function that stops at 0. Like with brightness, you can't have negative brightness. You can have brightness from 0 up to something high. Then I'm going to add a second convolutional layer with 64 filters. Again, the 3x3 kernel size. I'm going to stay with ReLU. Then I'm going to do this max pooling layer. These visual layers are they're sensitive to location. So if I have a dog up in the left corner and a dog in the right corner, it won't notice that those are the same thing. So the pooling reduces the dimensions of the space to bring those things back together so that a dog anywhere on the image would be identified by this particular set. Then I have to flatten that. I have to turn that two-dimensional array into a vector that can be passed onto the dense layers. Then I'm going to do another activation function again with 128 filters. And then finally, I'm going to do a softmax. We're just going to take all the results and push that down into something between 0 and 1. So it gives me the likelihood that each one of those things is going to be correct or not. So again, this is the simplest possible neural network defined using the traditional tools. Then after that, I have to train the model. I have to take that separate. I've already separated my data into training and test data. I then want to evaluate it. And finally, I have a model that I can deploy. Now I get to choose whether I want to put that up in the cloud. If I'm going to be in a connected environment, I can put that model up in the cloud and still be able to test it just fine. Or I may want to put it onto a local device, could be a phone, maybe it's a security camera or some other kind of IoT device that you want to work on. Then once I have the model deployed, I'm finally ready to make a prediction. So you can see where there's a lot of complexity. And if you're building these models by hand, this is weeks or months or years to make these things work well. So AutoML is going to make this a little bit simpler. So we still have to identify the problem, we still have to collect our data, but all of that model building, training, separating the data, all that gets handled automatically by AutoML. So once you have the data tagged, you upload it, you press a button for training, and then you can get predictions. And we're going to see an example of that in a minute. So just one more visual example. Let's say I plan routes for an airline. I'm using the best weather data that's available. These are models built by NOAA, various national weather services. But I have a fleet of planes flying around, and they have cameras on board. So I could be getting very, very much better local predictions by just looking out the window. So let's say I want to build a model that I can use to inform flights following along the same routes. So there are a bunch of different types of clouds. They all indicate different types of weather. And how do we do that? So I could take one of these images and I could submit it to the Standard Vision API, and it would say, yes, sure enough, what you have there is a cloud. It won't tell you what type of cloud, and it certainly won't tell you, be able to make a weather prediction based on that type of cloud. So let's see how we do this using AutoML. So this is a model. When we started building this, we put out a call amongst our DevRel group for people that had images of clouds. And we collected, 1,821 images. And we started trying to classify those. Well, it turns out we're all pretty good at coding, but we're not that great at identifying clouds. So we started asking around, and we found out that Google has a full-time meteorologist on staff. I did a big eye roll on that one. Seemed kind of silly, but it turns out there actually is some utility to this. This person is associated with Project Loon, which is the gigantic balloons that are intended to hover over a particular geographic location, like providing internet access after a natural disaster, for instance. So this person was very generous and went through and classified all our images for us. So you see underneath here, I have a cirrus cloud, cumulonimbus. On here, I can click on any one of these categories and see all the images that make up that particular classifier. If there are any unlabeled images, I can also see that, so I can go through and find the ones that may be able to improve my model. So once you have that, all the data, then you come to train. And we already have a model. It takes at least an hour to train, so I can't do that live, but let's show you what it looks like. So I'm going to click one button here to train a new model. I'm going to pick whether I want to do that for a cloud-hosted model or for an edge device. And let's just click edge here for a second, and I'll do continue. And for edge devices, you may have lots of memory, no memory, maybe a fast processor, maybe a slow processor. So you can change change parameters that define exactly how that model will be built to suit your particular device. Then once you do that, you're going to define a budget for that, and finally you're going to start your training. So say we've already done that, so I'm going to cancel that. And once we train a model, then we want to be able to evaluate to see how good it is. So I go to the Evaluate tab, and you'll notice there are a couple of curves up here for precision and recall. Those are standard methods that data scientists use for determining how accurate a model is. But I prefer this other way of looking at it, this confusion matrix down here. So this shows all the different classifiers we have. We have 5 here on each axis. And in a perfect world, you'd have a perfect blue line running down through the middle of that matrix, indicating that every time you had a cumulus cloud, it correctly identified it, for instance. It never made any mistakes. But in this case, we see we're not quite there. So for alto cumulus, 76% accuracy, cirrus, 92%, fantastic, cumulonimbus, 94%, but alto stratus, only 57%. And further, we can see that it gets confused with cirrus, cumulonimbus, and cumulus. So if I come back over here to my images, and let's just look at the numbers. So notice on Alto Stratus, I only have 134 images right here. And I have 500 cirrus, almost 500 cirrus, and almost 500 cumulonimbus. So that confusion matrix is a great way to determine where you might need more data to improve the quality of your model. Because ultimately, these things are built entirely on the data that is going into them. So once you have that, then you can go and you can test it. Now, I can do those here, but I'm going to go to a little Firebase app that we built for exactly for this purpose. I'm going to upload a cloud photo. And let's see how we do. Sometimes it takes a couple of seconds to make the first prediction. Oh no, did good right away. So this is so the model now has said that this is a cumulus cloud, 98% accuracy. And with our friend the meteorologist, he told us that cumulus clouds, that's great news because those show up on beautiful days when we have nice calm air and that we don't need to do any airplane rerouting in this case. Let's go get a second photo. And let's see what happens with this one. So now it says this cloud is a cumulonimbus, the 90% confident. Now, those clouds are associated with thunderstorms. So if you're in an airplane, you don't want to fly through that or really anywhere near it because there's often very, very high winds around that will make for a bumpy ride. So now by having these images, using this model, now we can use those images from the airplanes to predict very local weather along our particular flight paths. Okay, let me go back to the slides. Okay, so we've already seen that we have these pre-trained models, but we've also now seen AutoML vision, and there's also AutoML versions of natural language for understanding text, and for translation, and for video intelligence. Which is, the video intelligence is like the vision, but it works on videos. It will automatically break down a video into scenes and use those same kind of classifiers you saw in vision for identifying what is in each segment of that video. Then there's the new thing that just came out. It's in beta right now called AutoML tables. And that's what we're going to spend the rest of the time talking about. Well, I'm going to give a couple quick examples here. I forgot. So the natural language is... understands the semantics of the text. And what we see it using primarily is in detecting sentiment and in classifying content. You can build models that will automatically recognize types of documents, for instance. And for the ML version allows you then to incorporate your specific jargon from your domain. Again, the pre-trained model will do great on standard language that people use, but every business, every industry, every organization, every club has their own jargon that they use, and this allows you to incorporate that to get better models. So in this case, this is an organization called Donors Choose. It's a nonprofit that tries to match up the needs of schools with people who want to donate things to help the schools. They used to have a whole army of volunteers who would look at every single request from a school. They might be asking for pencils and paper or computers or sporting equipment. And they had to hand categorize those so that when donors came along, they could figure out what each donor wanted to give. Now they built this model using data that they already had, and were able to build this model with one click of a button. And now those incoming classifications are done automatically in 90+% of the cases using this now custom-built model. Translation, obviously for translating text from one language to another. The pre-trained model is great at doing normal translation. So like, I wish I spoke better Turkish. You're going to have to tell me whether that is a reasonable translation or not. I hope it is. Does it look pretty good? Okay, good. But if you wanted to be able to say that in Chinese, anybody speak Chinese or read Chinese in the audience? I don't see any hands. Well, you can do that here. And the important thing about this is that in the internet, you have customers or people utilizing your services from all over the world. You can't predict what language they're going to speak. So if you want to be able to communicate with them, to be able to sell them or support them, you want to make sure you can handle their requests in their native language. So AutoML Translate, why do we need to do custom training for Translate? Well, it's the same thing like with natural language. There's a lot of custom jargon that's used in almost every domain. So in this case, here's a customer, he's on his computer, he gets an error message saying no driver found. He goes on to Twitter and posts that the driver is not working. Well, how do we interpret that? So that's posted on our Twitter channel, and the driver is not working. It could be a golfer hitting with the driver club. Might be talking about the guy behind the wheel of a car, or in this case, it might be correctly identified as a device driver that he's having problems with. So this is being used by a lot of organizations for translating reviews or translating UI elements, so that if you're going to make localized versions of your apps, you can get the proper translation for all of those things. Okay, AutoML tables. So the vision and video and the text, they only account for a small portion of the potential uses that you'd want to apply machine learning to. Turns out the vast majority of the things you want to be able to learn from are structured data, something in tabular form. Just to make sure everyone understands what I'm talking about, this is just a spreadsheet, basically, or database output from a SQL query. Every single row here is one unique instance of something that will be part of the training model. And what we want to do is we want to be able to make a prediction from the data that we have. In this case, this is some data. I'll give a link to this particular data set later. In this case, this is a bank marketing data set that's been scrubbed and is publicly available. And this is being used to predict whether a particular customer is going to make a deposit or not. And we're going to see that in a little bit. But really, it's any spreadsheet data that's available. So you can see where this is used in any industry. In retail, you want to figure out whether you're going to run out of a product or not based on your sales rate. Finance, you may want to predict whether a credit card transaction is fraudulent or not. You have all kinds of data points on this, and by being able to build these models, you can now make better predictions, better use of this to improve the quality of your business. And even small improvements done at scale can have a dramatic effect going forward. So like in marketing, you might want to predict the lifetime value of a customer, or whether they're going to be able, or whether they might respond to a marketing campaign. So being able to use this and find those best possible targets allows everyone to do their jobs more effectively. Now, the problem with going into this type of model is that the range of choices you have to make goes up dramatically. You have this multi-dimensional range of choices that you have to deal with. So you have to first get your data ready. If you're not a data scientist, you may not be thinking about all the things that are important. You may have blank values. You may have incorrect values that skew your data. If a data scientist will go through that and scrub that data very, very carefully to make sure it's correct. You have to do feature engineering. That spreadsheet data contains different types of data. It has dates and years and numbers and yes/no answers and lists and strings and classifiers of just some small subset. You have to pick the right model for each one of those. You have to then figure out what's the best architecture to develop to build a model to address the problem you're trying to solve. Then you have all the different things like we showed earlier about activation functions and layers, and how do you do all that to get the best result. Then once you have it, you have to figure out all the possible combinations of ways you can tweak that to get the best result, until finally you're going to be out there and testing this. And you have to go through this over and over and over again, looking for small improvements over time. AutoML takes that and makes it much, much easier. You still have to collect your data, you still have to categorize it, but then you just drop it into AutoML tables with one click, and you select the column you want to train on. This is the value you want to predict, and then you're going to be able to build the model. So I mentioned it already, this works for numbers and classes and lists, and it has all these different guardrails for helping you manage that data correctly. Again, looking for blank values or data that are out of whack, or things like IDs where everything is unique and it's random, it's unassociated with the actual result. Then you have to go through and figure out all the different types of models you need to be able to select from very, very simple, like linear models, up through standard deep neural networks, and then on to ensemble models that are the most complex examples of models that are being built today. And there's great examples. Anybody use Kaggle? Good, awesome. So if you're interested in data science or machine learning, please check out Kaggle. They have contests, you can make money, and it's a great way to see how your skills are relative to the other people out there. We've been submitting AutoML models now to a bunch of Kaggle competitions, and it is doing pretty darn good. So in this case, you see some of the examples are up within the top few percent of the top hand-trained models that are there. So there's one specific example. Mercari is a Japanese marketplace. They want to be able to help their sellers predict what price to offer a specific product at. So they had all their backup data of what products sold for over time. So they published this data on Kaggle, had a competition to see who could come up with the best pricing model. This is an example showing how the quality of the model changed over time during the competition. The first few models came in up here, and then we saw some rapid improvement. As you get lower and lower, that means the models are getting better and better. So you see some pretty quick change as new models are put out by other people, or maybe people resubmit their models. Then it levels out quite a bit, where you're closing in on the fundamental noise of the data. You can't get much better than that in general once you see these plateaus. And then finally, we see out here at the end. Well, we submitted 3 different AutoML models. One was trained in 1 hour, one trained in 12 hours, and one trained in 24 hours. And you see even the 1 hour model was already at the plateau level. So those 1 hour training models can yield extremely high quality predictions from your data without having to become an expert in all those subjects. And AutoML tables is great if you really want to have at least 100,000 rows of data. We currently have it capped at 100 million rows. There's no fundamental restriction on that, actually. So if you need more than 100 million rows, talk to us, and we can probably make that available for you. So this is a good slide to take a picture of if you want to check out this data set that we're going to take a quick look at. I've got 3 minutes. I got a jam. So let me just go ahead and drop over here into AutoML tables. So I've already uploaded a data set, and I'm going to go over here now. So if you want to import a data set, you can do that from BigQuery. You can do it from cloud storage, or you can upload it right from your computer. Once you do that, you're going to train it. And even before you train it, when you import it, you learn some interesting things about the data. So I can click on some of these things, and it shows me information about each one of those fields. So I can learn a lot about the data from scratch. Then once I'm there, I can have multiple models, look at accuracy. I'm going to go here to the full evaluation. And again, I have those precision and recall graphs. But I also have the confusion matrix, which we looked at earlier. In this case, it's really, really good at predicting 1. So we have 2 values for this. 1 indicates that the person did not make a deposit. 2 indicates that they did make a deposit. It's really, really good at predicting 1, not so good at predicting 2. That's because the data is highly skewed. There's many more values of 1 in the data set than there are 2. Another great example of how you want to make sure you're matching your data to the model you want to be able to predict. Then down here, this shows feature importance. So this shows which of the features of your data set are most highly correlated with the prediction you want to make. So in this case, duration, how long the person has had an account, is the most important feature in determining whether someone is going to make a deposit or not. So let me just go right over to test and use. You can do batch prediction. You can upload a spreadsheet of additional values. You can make predictions across the entire spreadsheet. Or in our case, we're going to do online prediction. So I can do this from JSON that gives an API reference for this, or we're going to do it right here in the table. I'm going to do this first prediction using this 1 row of the data. It comes in and says it is 99% confident that this person is not going to make a deposit. Now, we know from looking at that import data that duration is the most important factor. So let's look at how long this person's has had an account. Only 13 days. So let's make this 2,000 days. So let's make it a few years and see if that makes a difference in our prediction. We'll do a new prediction. And sure enough, now we're 76% confident that this person will be making a a deposit. So I hope everyone can imagine how this can be used in your businesses, your organizations, your customers, to be able to gain real value by taking this tabular data that's so important for all of our functions and using it to make predictions. I've got some more slides on here that I'm not going to be able to discuss. I'm going to get back down here to the end. And so this is showing that you can use pre-built models, you can do hand-built models, and now with AutoML, you can do that without having to become an expert. Okay, so there we go. There are some links up there you can use to learn more about these subjects, and I'll be hanging around for the rest of the afternoon, so I look forward to talking to anybody who has additional questions. Thank you very much.